Okay, Math 352, we're up to lecture 18, and today we're going to be looking at our first topic in quadratic programming, and we're going to have a bit of an intro, and then look at some of the simpler cases, and these are unconstrained and equality constrained quadratic programming. Okay, before we get into this, we need a little bit more mathematical background. So we're just going to take the briefest of brief looks at what are called convex functions. Now you may or may not have come across these before. Okay, so if I'm talking about a convex function, then my kind of loose definition is as follows. Okay, a function is convex if f of theta x plus 1 minus theta y is less than or equal to theta f of x plus 1 minus theta f of y. Okay, where x, y, for the purposes of what we're doing, are an Rm. Okay, so that's the definition. Doesn't give us much insight yet. Oh, one more thing. We should also say that theta is in the interval 0 and 1. Okay, so what can we say about this? What can we do with this thing? Okay, let's draw a picture. So I'll stick with a 1D case at the moment. Let's say we've got a function of one variable. So here's x along here. And I'll mark my points x and y along this axis here. And I've got a corresponding point f of x and another point, let's just move it slightly off that one, f of y. Okay, so we could draw these lines here if we really want to. Okay, so what does this say, this definition here? Well, if I look at the argument to f here, I've got theta x plus 1 minus theta times y. Now hopefully you'll recognize that as the line segment that joins x to y. Now in this case it's just a line along here, and in a higher dimensional space, then it would just be the line segment joining up the points x and y. Okay, when theta is equal to 0, you just get y, and when theta is equal to 1, you just get x. Make sense? Cool. Okay, so this is called a convex combination of x and y, and it just corresponds to the line across here. Okay, so let's just we'll take a point, and this will be theta x plus 1 minus theta y. Alright, what about this thing here? Theta f of x plus 1 minus theta f of y. That's the same kind of argument. So that's also a convex combination of f of x and f of y. And the set of all these points with theta between 0 and 1 gives us the line between f of x and f of y. So put together, what this says is that if I draw this line, okay, so there's theta x plus 1 minus theta y here. The corresponding point here would be theta f of x plus 1 minus theta f of y. Okay, so what I'm saying is that my function between these 2 points has to sit below this line segment. So my function has to look something like that. Has to be curved upwards. Okay, so the way you think of it is you take any 2 points in your function, draw a line segment. The function has to sit beneath or on that line segment, not above it. So for any 2 points x and y, that has to be true. So a convex function, just think of it as a function that's curved upwards. Okay, so in 1D it just looks like a curve like that with a positive second derivative. In 2D it has a function that kind of looks, I guess, kind of bowl-like. Okay, so if I take 2 points in my bowl, say one here, and another one over here on the far side, then if I draw the line segment joining those 2 points up, that sits above the bowl between it. Okay, so you can imagine there's also this curve along the bowl that sort of corresponds there. Okay, and that red line segment always sits above it. So our intuition for a convex function is that it's something that's always curved upwards. Okay, right, let's just have a look at some more examples. Is this function here convex? Let's have a look. I'll just see if I can draw it. Okay, if that was our function, is that convex? Answer, no. It's fine there. It's fine there. But if I, for example, took these 2 points, then my function doesn't sit below it, so it's not fine. Okay, so that function there is not convex. So that's basically what we need to know about them. They're really nice in optimization problems because they have a really good property, which is, well, question, is it possible for a convex function to have two distinct local minima? Okay, is it possible to have a local minimum here and one somewhere else? And the answer is quite clearly no, because if you drew a line segment between the two, you'd have part of the function sitting above it. So if you have found an optimum or a local minimum, can find a local minimum, then it's global as well. There are no other local minima. So they're this really nice class of functions that are very easy to optimize in the sense that if you find an optimum, then that's the global optimum of the entire function. There's nowhere else that you can't, there's guaranteed to be nowhere else that's lower than that point. Okay, so we have some optimality conditions. And these are basically what we looked at last time with our Hessian matrices being positive definite. So our two optimality conditions are that our gradient is equal to 0, so it should be an x star. Okay, if our function has 0 gradient, then we've found something, and our Hessian is positive semi-definite. Okay, so remember, if I say that a matrix is greater than or equal to 0, I mean positive definite or positive semi-definite. Okay, so this is actually true of any function. Of any function f, these conditions will guarantee that you've found a local minimum. Okay, if it's convex, then it means you've found a global minimum as well. Okay, so we'll take a sort of prototypical convex function, and that's a quadratic form. So a quadratic form looks like this, and I'm just going to be focusing on real valued functions. Your average for quadratic form looks something like this. F of x equals a half x transpose px plus q transpose x. Okay, so a couple of things we need to know how to do. What is the gradient of f of x? Okay, so I'll just work the gradient out on the side here, just to make the left-hand side stay nice and neat. So I'll just bring up an example. Let's just do a 2 by 2. Assume that the matrix P is symmetric. So 1, 2, P, we'll call that 1, 1, 2 as well because it's the same, and P 2, 2 plus Q transpose x1, x2. Okay, so df dx1. In fact, so before I do that, let's expand this thing out. Okay, it's probably more detail than we really need to do here, but it's good to see it done in full just to convince ourselves that what we're doing is not wrong. Plus, let's see, p1, 2, x1, x2, there are two of them, multiplied by half gives us 1, plus half p2, 2, x2 squared, plus q1, x1, plus q2, x2. Okay, there's no benefit for writing out our quadratic form in full like this, except that when we differentiate it, it's a bit easier to see. So df dx1, which is the first component of our gradient, is p1, 1, x1 from this term here, plus p1, 2, x2 plus q1. df dx2 is equal to p12x2 plus p22, sorry, what am I saying? p12x1 from this term here, plus p22x2 plus q2. And we can write that in matrix form as, well, this here is just p times x and plus q. So the gradient, how about we write it like this? That's our gradient, that's the vector form, and we can write it as a simple matrix expression like this. So it has this nice sort of matching format to what you expect from single variable functions. Okay, and the Hessian, oops, superscript. How do we get that? Well, we just look at this matrix here. And so we've got d squared f dx1 dx2, sorry, dx1 squared, I keep making mistakes today, dx1 squared plus d squared, not plus, d squared f dx1 dx2, d squared f dx2 squared, and d squared f dx1 x2 again. Okay, which equals, okay, if I'm going to take the derivative of, well, you can see that we're going to have p11 only. Okay, when we take the first derivative of this entry with respect to x1, everything but the p11 is going to vanish, and you can quickly fill in the rest, and you get back to your matrix P. Okay, so that's what a quadratic form looks like, and that's what its gradient and Hessian look like. So the Hessian is just the matrix itself, and the gradient is given by px plus q. Okay, so we'll look at our first case of quadratic programming. Okay, so the only difference between quadratic programming and linear programming is we now have a quadratic objective instead of a linear one. Okay, so whereas for our linear programming we had C transpose X as our objective all the time, now we're going to have a quadratic form as our objective, and we're trying to minimize that. So we're going to start looking at unconstrained quadratic programming, which is just minimizing the objective with no constraints. Okay, so minimize over x 1/2 x transpose px plus q transpose x. I could add on a constant if I wanted to, and that's all. Okay, so we're trying to find a minimum of that. So what I'll do is I'll break this down into a number of cases, and we'll see what solutions, if any, we have for each case. So here's our problem. A nice, simple to state one. So first case, what if P is not positive semi-definite? Now remember, positive semi-definite includes positive definite, so that means it's not positive definite either. Okay, so what we do, we pick an x0 such that x0 transpose p x0 is less than 0. Okay, if it's not positive semi-definite, that means we can find an x0 such that that's true. Then f of t x0 equals 1/2 x0 transpose p x0 times t squared plus q transpose x0 times t. And you can see this function here, the coefficient of the t squared is negative, so we've got an upside down quadratic. As t goes to infinity, our function is going to go to negative infinity. F of tx0 goes to negative infinity as t goes to infinity. Okay, so there's a nice negative case to start with. If our matrix is not positive semi-definite, okay, then basically we can find the next naught that means that our function doesn't have a minimum. Okay, so next case. Let's go for a positive one this time. P is positive definite. Okay, our optimality conditions are gradient of f is equal to what? The gradient of our function is equal to px plus q, and our Hessian is equal to p. Okay, and so for optimality, the gradient has to be equal to 0, and the Hessian has to be positive definite. Okay, this is a local minimum. Okay, at x star, so just solving this equation here, x star equals negative p inverse q. Okay. Moreover, our quadratic form, you can prove this for yourself if you like, is convex, so this is a global minimum too. Okay, just think of a parabola. A parabola is convex. You can just join any 2 points on a parabola and the line segment will be above the curve. Okay, same with a higher dimensional one. It's the same, you basically get a bowl or a higher dimensional looking bowl. Okay, so our objective is convex. We've satisfied the optimality conditions. Our Hessian is positive definite, and we can solve for a point with 0 gradient because a positive definite matrix is invertible, and so we're good. Okay, so it's a unique stationary point. Okay, next case. So we've done positive definite. We've done not positive semi-definite. The last case we need to look at is if P is positive semi-definite. Okay, and I'll say strictly, and that means that there are some x's such that x transpose px is equal to 0. So optimality means grad f equals 0, which implies px equals negative q, and Hessian is positive semi-definite, which is satisfied by definition. Okay, so the Hessian, let's just rearrange that slightly. Hessian, which don't forget, for a quadratic form, the Hessian is just p, has to be positive semi-definite, and it is. Okay, so minimizes, if any, satisfy p x star equals negative q. Okay, so let's have an example. So in this case you can actually have some cases where you can find minimizers and some where you can't. So let's have an example. This matrix here is clearly positive semi-definite because its eigenvalue suggests its diagonal entries and one of them 0. The rest are positive, and our q is equal to 1, 0. And we want to minimize over x 1/2 x1 squared, it will be, plus x1. Okay, so if we want to solve px equals q, let's bring it back up again. Px equals q, we get 1, 0, 0, 0, x equals 1, 0. This is in row echelon form already, so we say let x2 equal t, therefore x1 and x1 is constrained to be equal to 1, sorry, not 0. So any point 1t is a minimizer. Okay, because we can solve this, any point satisfying that is a minimizer. Okay, another example. We'll have the same p, and now we'll have q equals 1, 1. Okay, px equals q is inconsistent, because we've got a 0 equals 1 on the bottom line. Inconsistent. So we have no solutions. Okay, so we can actually see this directly. So our problem is minimize 1/2 x1 squared plus x1 plus x2. Okay, using x1 equals 0, x2 tends to negative infinity. Then our objective also goes to negative infinity. We can see f of x has no minimizer. Okay, it's unbounded below, we've got no minimizer. Okay. So, that's basically our set of cases of unconstrained quadratic programming. There's not really much to do here, it's just minimizing a quadratic. So, we've found that sometimes, if it's positive semi-definite, then we sometimes have minimizers. If it's positive definite, we have a unique one. And if it's indefinite, or negative anything definite, then we don't have a unique minimizer. We don't have a minimizer at all. It's unbounded below. Okay, so that's all rather straightforward, really. So we're going to move on to the next step of difficulty up, and that is equality constrained quadratic programs. Okay, so I always talk about quadratic programs as QP, likewise quadratic programming, and the equality constrained case we call EQP for short, because I don't want to write equality constrained quadratic programming down all the time. So now our optimization problem looks like minimize over x, just like our linear programs. Our objective, f of x is equal, f naught of x is equal to half x transpose px plus q transpose x. And now we have a set of equality constraints. Okay, so let's just specify a few conditions here. Just like in linear programming, we're going to look at m by n matrices A with m less than n. Okay. No, it needs to be less than n. Otherwise, if we have no, so otherwise ax equals b determines. If n equals n, then ax equals b is solvable. Determines x or no feasible point exists. In fact, before I said that, I should also say that, as usual, the rank of our matrix A equals m. Okay, it's full rank. We've got no redundant constraints in there. Okay, so what happens in this case? Well, first I'll say something here. Actually, no, I won't say that. We'll discover it. Okay, so let's just have an example We'll start with a really small example so we can just see what types of things can happen, and then we'll look at how to actually do it. Okay, so minimize x1 squared minus x2 squared subject to x2 equals 0. Okay, although my matrix P, we would write that out in our standard sort of format, a matrix P would look like that. Oh, sorry, I wouldn't. Don't forget the factor of half. Would look like that. It's got a negative eigenvalue and a positive one, but we're constraining x2 to be 0, so this negative entry never comes into play. So P is indefinite, but we have a minimizer at 0, 0, because the indefinite part, or the negative part of P, is basically constrained out of the equation. Okay, so when we're dealing with equality constrained quadratic programs, we don't necessarily have a positive definite matrix, but so long as the matrix is positive definite on a subspace, in this case it's a space of x1, or the subspace x2 equals 0, then we can still minimize our objective. Okay, so this is sort of the basis behind this method that we're about to look at. So what we're going to do is we're going to look at what we call the null space, or the QR method. Okay, so I'll get a new fresh page. So look at the null space. So if I refer to the null space method, or the QR method, then this is what I'm about to do, because there's actually another way we're going to solve these a little bit later. Okay, so first we're going to look at the equality constraints. Okay, so I'm not touching the objective yet. I'm just going to look at what my equality constraints imply about x. Just remember, A is this shape here. Okay, so take the QR factorization of, remember we always take a QR factorization of a tall skinny matrix, so the QR factorization of A transpose, and I'll write it down as the full QR factorization, equals QR, just to remind you, Q hat, Qn, R hat, which is square, and 0. So AX equals B, that becomes R transpose Q transpose X, which in turn can be expressed in terms of the reduced QR factors, R hat transpose Q hat transpose X equals B. Now we'll write X. Okay, remember how we often can write our X down as a, sorry, start again. Our Rn, a basis for Rn are the columns of Q, okay, which is the columns of Q hat and columns of Qn put together. So we can write X down as components with each of those pieces as bases. So we write X as X equals some linear combination of the columns of Q hat plus some other linear combination of the columns of Qn. So R hat transpose Q hat transpose X equals R hat transpose Q hat transpose Q hat U plus Qn V. Now Q hat transpose Q hat is the identity, Q hat transpose Qn is 0, so that equals R hat transpose V, which equals B. Sorry, R hat transpose U, which equals B, so U equals R hat inverse transpose B. Okay, so U is fixed. V is completely free. So this is basically the method of working we did for our least squares problem earlier, where we have an underdetermined system. In that case, we were trying to minimize just the norm of x, so we set our v was equal to 0. Here we're trying to minimize something different, which is going to be a quadratic form, so we're not going to automatically set v to be equal to 0. V is the thing we're going to try and vary to minimize our objective. Okay, so let's just write down what x is now equal to. So x equals q hat u plus q in v, which equals q hat r hat inverse transpose b plus q in v. And just for convenience, because I don't want to keep writing this down, is equal to x hat plus q in v. Okay, where x hat is fixed. So we're free to vary v, and that will have some influence on our objective. The other part of it, which involves u, is fixed by the equality constraints. That's why this is called the Nullspace method, by the way, because v is the part of x. V gives us, where is it gone? V gives us the part of x here that is in the null space of our matrix. Okay, so our objective is f of x equals 1/2 x transpose px plus q transpose x. We're going to plug that in. So f of x equals something kind of nasty. So wherever I see an x, I'm just going to stick in my new expression for x. So I'll get 1/2 x hat plus q in v transpose times p times x hat plus q in v plus q transpose times x hat. You can see why I didn't want to write down this all the time. Plus q in v. Good. And we want to rearrange this into a quadratic form in our v, because v is the thing that we're free to vary here. Everything else is a constant. So we want to just basically expand this all out and then refactorize it into a quadratic form in v. So that equals 1/2 v transpose. You can check this working for yourself. q in transpose p q in v. That deals with this term here. That's the only quadratic thing in v. Now I'm going to look at the linear part. X hat transpose p q in plus q transpose q in. That should account for all of the v terms, the linear v terms. Then plus a constant, 1/2 x hat transpose p x hat. Don't forget x hat is just a constant, it's not a variable anymore. Plus q transpose x hat. Okay, this is an unconstrained quadratic form in v. Okay, so let's just have a look at our quadratic form again. We've got v transpose times a matrix times v. We know if this matrix here is positive definite. Okay, it's not p is positive definite, it's this matrix inside our second quadratic form. If that one is positive definite, then we have a unique minimizer. So if qn transpose p qn is positive definite, by the way, another way of saying that is that p is positive definite on a subspace, which in this case happens to be the null space of A, then we have a unique minimizer given by V equals negative P inverse Q, remember? So I'm going to do the equivalent thing here. Negative Qn transpose P Qn inverse times our vector piece. X hat transpose P Qn plus Q transpose Qn. Okay, it looks horrible, but basically it's just what we did earlier. We've got an unconstrained quadratic here. If we relabeled these things as single letters, then it would look nicer on paper. That's okay. So that gives us our V that minimizes our quadratic form. So finally, our optimal X is equal to our X hat plus Qn times V star. Okay, so this one's got a wee bit of an amount of matrix algebra involved here, but in essence we're just solving another quadratic problem. We use the QR factorization to reduce our problem down into an unconstrained one in the null space, because the QR factorization let us basically fix m of the variables to satisfy the constraints, and the remaining n minus m degrees of freedom were accounted for in this factor v, and we managed to derive an unconstrained quadratic for v, which we know how to solve based on our previous work. Okay, well that was fun. So I think I might actually leave it at that, because we're going to... Actually, no, I won't quite. We've got a wee bit more we can do. There is another way, in fact, of doing this. If our matrix is positive definite, then... So this is another method, the KKT method. For EQP. Okay, so if we've got an optimization problem, minimize f naught of x subject to ax equals b, where f naught of x is convex, then the optimality conditions these are conditions that will give us an optimum, are given by the following equations. Now, unfortunately, I can't really go into any detail on the theory of these things because we just don't have enough time. But they're given by the following equations, known as the KKT, or Karush-Kuhn-Tucker conditions, known as conditions. Okay, and these are that, in fact I won't even say that, I'll just say hi of x. Okay, so we've got a convex objective, and hi of x equals 0, f naught of x is convex, hi of x is affine. Okay, that means a straight line, but possibly with an offset from the origin. Then the following conditions, if we can solve them, will give us an optimum for this problem. And that are these. The first one is obvious. Any optimum we have has to satisfy the equality constraints. Okay, so that's feasibility. Okay, and the gradient of the Lagrangian, it's the same Lagrangian as we use for linear programming, at optimality, so that's the optimal Lagrange multipliers and the optimal x's, has to equal 0. Okay, so if we can solve those equations, then we can solve our problem. Then we've found a solution to our problem. So these conditions are necessary and sufficient for global optimality for a convex problem. Okay, when we're dealing with convex optimization problems, we always have a convex objective, affine equality constraints, and convex inequality constraints, which we're not up to yet for a convex problem. Okay, so what do they look like? So for an EQP, which is minimise over x, half x transpose px plus q transpose x, with p positive definite and subject to ax equals b, these conditions become ax star equals b, and gradient of f, which we know as px star plus q, plus an optimal Lagrange multiplier multiplying each of our equality constraints, or the gradient of them, so that's why the b's go away, is equal to 0. Okay, and these conditions can be written down in matrix form. We basically have a set of equations to solve in our optimal x's and our optimal n's, our optimal Lagrange multipliers. And this is going to have a negative q up here, so this is from our second equation. And we're going to have a 0 down the bottom. This is from our feasibility. So what have we got? This is a set of m plus n equations and m plus n variables which can be solved. Okay, so if p is non-singular, which it will be if it's positive definite, then this completely determines. In fact, sorry, that's not quite the right thing to say there. If the matrix, what we call the KKT matrix, is non-singular, then this completely determines the solution. Okay, so I think we've got time for a quick example. This is a much easier method to do by hand, by the way, than the QR method. Okay, the QR method is very much suited to solving on a computer. If you've got a small problem that you want to solve by hand, then this is a lot easier to write down and solve as a system of linear equations. However, the QR method is a bit more general. We've required p to be positive definite here. We haven't done the same thing for the QR method. The QR method takes into account that p does not have to be positive definite on the null space, kind of better than it does for the equality constrained method, the KKT method we've presented here. Okay, so let's do a quick example. Example 3, KKT. Okay, so I'm going to look at p equals 2, 1, 1, 2, q equals negative 6, 7. And we've got a single equality constraint, ax, oops, not right, b equals 3. So remember doing minimize half x transpose px plus q transpose x subject to ax equals b. Okay, well let's just put all the pieces together. So we know that our matrix has got, if we just skip back a page, P in the top left, and then it's got A transpose in the top right. It has A in the bottom left. Okay, it's a symmetric. It's always going to be a symmetric matrix. And what does it have in the bottom corner? It has 0. And then we have our variables, which in our case will be x1 star, x2 star, and our optimal Lagrange multiplier. On our right hand side, we have negative q, see, negative q, and then we have our b. Okay, now this is actually already in a kind of back to front row echelon form, so we can just solve this by substitution. So we have, let's see, x1 star, they won't always turn out to be, you usually need to do a little bit of row operation or something first. x1 star is equal to 3, sorry. x1's second equation says x1 star plus x2 star equals negative 7. Therefore x2 star is equal to, take away 3, negative 10. And the final one says x1 star plus x2 star plus nu star is equal to 6, which implies that nu star is equal to, well, it's the x1 star plus x2 star. I'm doing this wrong. I'm doing this wrong. Back up a moment. Let's try this again. If I could read a matrix properly and write down the equations properly, I'd see the x1 star plus 2 x2 star is equal to negative 7. Therefore, x2 star is equal to negative 10 divided by 2, negative 5. That's better. And finally, 2x1 star plus x2 star, now I can read equations, that's positive, is equal to 6. Gives us finally that nu star equals, let's see, 2x1 star is 6, take that away will give us 0, x2 star is negative 5, add that on will give us 5, so nu star is equal to 5. Okay, so that about wraps up what we're going to do on equality constrained quadratic programming. We'll finish our topic off next time, or this particular part of it off next time, by looking at shadow prices interpretation again. And then we'll go on to the more general and more difficult case, which is that of inequality constrained quadratic programming. Okay, so that's me signing off. I'll see you back in class next week. See you later.